So this is about cumulative binomial probabilities. I'll explain what they are in a few minutes in case you don't know or you've forgotten. Normally students of this area are given a booklet that contains the cumulative binomial probabilities, but here I'd like to explain an alternative way of working them out using one of the Vedic sutras. So first of all, let's look at Pascal's triangle. You may be familiar with this. You start with 1 and you can imagine zeros everywhere else, and then you simply add two numbers like 0 and 1 is 1, and 1 and 0 is 1, and then you add these up, so you have 1 and 0 is 1 here, 1 and 1 is 2, 1 and 0 is 1, and you go on like that and you build up the famous Pascal's triangle, and you can go as far as you like. Quite often we see this triangle in a different form where the whole thing is pushed over to the left like this. The numbers are the same, we've just leaned it over to the left like that. And this is the form we're going to be using. And it's well known that the coefficients, or the values in any row of Pascal's triangle give the coefficients in the expansion of a plus b to the n. So, for example, if you wanted a plus b to the power 6, if you look at the sixth row here, we'll call that the sixth row, these values are in fact the coefficients that come up, 1, 6, 15, 20, 15, 6, 1. And so rather than multiply all that out, you could use those coefficients in Pascal's triangle to write down the answer. You'll see the a to the 6 goes down 1 each time, a to the 5, a to the 4, and so on. And the powers of b go up, so b to the 0, b to the 1, b to the 2. It's the coefficients that are really needed in order to write down the expansion of something like this. So that's a well-known application of Pascal's triangle using the rows. Binomial probabilities are where we've got a situation where there are two possible outcomes. So one example that illustrates it quite nicely is if you are an archer firing arrows at a target. Suppose you have 6 shots at your target, so we say n is 6. And suppose the probability of hitting your target is 0.2. You're not a very good shot. Then you can work out the probability out of 6 hits of various outcomes. So, for example, if you fire the arrow 6 times and you get 6 hits, the probability of that will be 0.2 to the power 6. 0.2 to the power 6. 0.2 times itself 6 times. The probability of 5 hits and 1 miss is given by this. Here are your 5 hits, 0.2 to the power 5, and your miss, the probability of that is going to be 0.8 because 1 minus 0.2, and there are 6 possible ways in which it could happen, because that miss could happen in 6 different positions. Your first shot could be a miss, or your second shot could be a miss, and so on. There are 6 ways. So that's where that 6 comes in. And if we wanted to go further and think about maybe 4 hits and 2 misses, the probability of that actually happening is given by this. So there's your 4 hits, and there's your 2 misses. And in fact there are 15 ways that can happen, because the 2 misses can be distributed in 15 ways amongst the 6 shots. And so on. And you'll see the numbers here correspond. So we've got 1 here, 1 times 0.2 to the 6, which is the first number there. And then we've got the 6 here, which is this, and the 15 here, and so on. And this is also well known that we can use the values in a row of Pascal's triangle to write down binomial probabilities. Now when it comes to cumulative probabilities, which we're on to here, we're talking about the probability of 6 hits or 5 hits. We're accumulating them, 6 or 5. And that means the probability of 6 hits plus the probability of 5 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. Or the probability of 6, 5 or 4 hits, which must be these two added up. There they are. There's those two added up. would be the probability of 6 hits plus 5 hits plus 4 hits. This is 6 hits, this is 5 hits, this is 4 hits. We've got them up here. Now suppose, just to make it a bit simpler, we're going to replace the 0.2 with the letter A and the 0.8 with the letter B. Okay, so this is the same as that with A equal to 0.2 and B equal to 0.8. And we note, of course, that A plus B has got to be equal to 1. So this is the algebraic form of the answer to the probability of 6, 5 or 4 hits. Now suppose we take out the common factor of a to the power 4, like this, we get this. Now we can write it like this, because if you look at this bracket here, this square bracket, if you expand the a plus b squared, you'll get a squared plus 2ab plus b squared. The a squared is what we've got here. The 2ab combined with the 4ab gives you the 6ab we've got here, and the b squared with the 14b squared will give you 15b squared. So this is just a different form of the same thing. And of course we've said that a plus b is 1. So we get this. 1 squared is 1. And now we're going to take b out as a common factor of these two terms, like this. And note that 4a plus 4b, if a plus b is 1, 4a plus 4b 4. So that's that 4 there. So I've taken a 4a plus 4 of the b's out of here and made it into a 4, so I've got 10 b's left. So what's happened now is I've got this alternative form, alternative to this. So this is our new expression, and this was the original one. And this is simpler, as you'll see in a moment. So that's what this paper is about, really, the alternative form going from here to here, which is actually easier to use. So there is that last result. Probability of 654 hits is given by this, and I've highlighted the coefficients there, 1, 4 and 10, which you'll see are the coefficients in the column here, 1, 4, 10. So it turns out that for cumulative probabilities, the columns can be used. For individual probabilities, we can use the rows in Pascal's triangle, and for the cumulative probabilities, we can make use of the columns. So for single probabilities, we use the rows in Pascal's triangle, and for cumulative probabilities, we use the columns. Now let's just compare these two results. This here is the probability of 6, 5 or 4 hits by the method where you just add up the three probabilities individually, and the coefficients are given by these numbers here, And the alternative form is this one, in which we've got the 1, 4, 14, the numbers in this column. If you study it, you'll see quite quickly that there are 17 multiplications involved in here, but only 7 in here. So there's a big saving in the calculating power, whether you do it mentally or on paper or with a calculator. There's a lot of saving, and this is followed through with other such cumulative probabilities too. So let's look at all the possible cumulative probabilities we could have for an n of 6 and a probability of a hit being A. We could have just the probability of 6 hits, which is a to the 6, and the coefficient there is 1, which corresponds to this one here. Or we could have probability of 6 or 5 hits, which turns out to be this, and the coefficients here are 1 and 5, which is this column. The next one is the one we actually worked out just now. Probability of 6, 5 or 4 has got coefficients 1, 4 and 10, and that's those coefficients there, and so on. We can use the Vedic Sutra, only the last terms, to help us write down these expressions. So in the case of the probability of 6, 5 or 4 hits, we look just at the last number there and notice that it's the power of the A, and the same with all the others, 5, 5, 3, 3 and so on. So that's easy. Also notice that because we've got three values here, there are three terms inside the square bracket. But that 4, the last term, also gives us the column that applies. So it's the fourth column. We get 1, 4, 10. And those are the coefficients that go in here. So we always have the A outside and the B inside. And the coefficients are given by the appropriate column in Pascal's triangle. For 6, 5, 4 or 3 we get this column, 1, 3, 6, 10, and so on, like that. Now, we wouldn't really want to work out the probability of 6, 5, 4, 3, 2 or 1 hits using this formula. Because we like to do things easily, we'd work out the probability of the number of hits that's missing from here, which is probability of 0 hits, and take that away from 1. So an alternative way of working this out would be to work out 1 minus P0. And P0 means no hits, which is p to the power 7. And that's given by this number here. And if we wanted to get this one by an easier method, the two missing values there are 0 and 1. And it's easy enough to show that that's equal to this expression. Notice the connection between these two. Here we have a squared, where 2 is that number there. And here we have b instead of a. We have a inside the square bracket instead of b. The power on b is also given by the last term here, but we have to take that number from our value of n, which in this case is 6. So 1 from 6 is 5. Notice also the way the pair of probabilities here behave. We had previously, and now as the red ellipse goes to the left, the yellow ellipse goes to the right. And the next one, they move closer together like this, and that's the probability of 0, 1 or 2, given in the red, with the red coefficients, b to the fourth here, where 4 is 6 take away 2, and the 1, 4, 10 is the numbers in the fourth column. And similarly, here they will cross over. Now the red one's on the left and the yellow one's on the right, and so on. Just go through those again so that you can see. Note how the ellipses change places. Like that. Now let's take another example. Suppose now our n is 7 and the probability of a hit is A, and we want the probability of 7, 6, 5 or 4 hits. We focus on the last term there, the 4. That tells us that we've got a to the power 4. So we go down to the 7th row in green there, and we'll highlight the column that starts with a 4. And so the probability of 7, 6, 5 or 4 hits is going to be a to the 4 times this expression using those coefficients in that column, 1, 4, 10, 20. So these are quite easy to write down and fairly easy to work out too. You just use your b, multiply by 20, add 10, multiply by b, add 4, multiply by b, add 1, and multiply by a to the 4. To take another example, the probability of 0, 1 or 2 hits. Well, this is our alternative system where we use those red columns. The last term here is a 2, and we're working from the other end now, so we take the 2 from our n, which gives us 5. So we're going to start off with b to the 5. And we're also going to use that 5 to get us this column of numbers here, 1, 5, 15. And so we're going to have 3 terms in there, just as here we had 4 terms, 1, 2, 3, 4, corresponding to those four numbers, we can have three terms, and they're going to be 1 plus a into 5 plus 15a. So, cumulative binomial probabilities can be found more easily using the columns in Pascal's triangle. And the sutra only the last terms indicates the pattern that applies in each case.